Hi everybody, welcome to the section 3.1 video. In this section, we're going to take another look at linear models, okay? Differential equations as mathematical models. So we're going to learn in this section how to solve exponential growth and decay models and solve Newton's law of cooling and heating model. Okay, so we're going to take a look at a couple different exponential growth and decay models and then finish up with Newton's law of cooling and heating. Okay, so this is bringing us back to section 1.3. In section 1.3, we learned a variety of first order differential equations that were used for mathematical models. So we were given a couple situations and we were able to develop differential equations to make them mathematical models. So we're going to be able to now solve these mathematical models. And the two main we're going to look at today are exponential growth in various situations and Newton's law of cooling and heating. So let's introduce the most general form of exponential growth and decay. So we've seen this before. We've developed this actually, that the initial value problem for exponential growth and decay is dp over dt equals some growth constant k times the function p, okay, with an initial condition of p naught. Okay, so that is our initial value problem. And remember that this is our initial population. At time zero, that's our initial population. And so, yeah, this is a model for exponential growth and decay. K is our constant of proportionality, and growth if we have our population is growing if we have K greater than zero, and decaying if we have K less than zero. Okay, so we developed this from this statement that we've seen before that the growth rate of a population is proportional to the current population. So we developed this back in section 1.3. Okay, that's where we developed this differential equation. And now, since we've learned the tools of how to solve differential equations, whether it be graphically, analytically, or numerically, we now have the tools to solve this differential equation. So let's go ahead and do that. So here we have the differential equation dp over dt equals k times p. Okay, independent, p is my dependent variable, t is my independent variable. But we can go ahead and solve this. And the type of differential equation this is separable. It's a separable differential equation. So what I can do now is move a couple terms over. So what I'm going to do is divide both sides by p and multiply dt to both sides. So what I would end up with is dp over p equals k dt. And so this is separable. I have all my terms I need on both sides. They're separated. So now we can go ahead and integrate. So when I integrate dp over p, it turns into natural log of p, absolute value. And then k is just a constant. So what we do is pick up a t and plus c. So we want to solve the differential equation. So remember, when we have the natural log, we want to base e both sides. So the natural log cancels out, and I'm left with just p. Okay, so we have e to the kt plus c. So a couple things here that we have absolute value p, but one thing we can do is get rid of absolute value because Well, we're talking about population here. The population is never zero or negative. It'll always have to be positive, okay? Otherwise, this model does not work. So we can just get rid of that population P. And one thing we can also do as well is separate out our exponent with exponent laws. We can separate those terms out to be e to the kt times e to the c. And then e to the c, well, we can just make that that's just a constant, so we can write it as another constant. So we'll call it a. That's what our textbook calls it. And we'll say p equals, we'll bring that up to the front, a e to the kt. Okay, so that is our setup. But remember, we have this initial condition to worry about. Okay, but what we're going to do now is just plug that in. So let's come back over here. We're going to use this initial condition at time zero, our population is P naught. And we're just going to plug that into our solution that we just found. So we'd have P naught equals A e to the K times zero. And this would be P naught equals A e to the zero, or e to the zero is just one. So P naught just equals A. Okay, so coming back down over here just to find some space, therefore, the solution is P of t equals P naught, our initial population, e to the kt. And that is our solution to growth and decay. So the great thing about this solution is that this will always be our solution to this growth and decay model. We don't always have to go out and find it. We know this will be our solution, and we can always just adjust to whatever the problem is giving us. So that's the great thing about this model. So if you look to the graph right here, just some intuition to it is that, for our proportionality constant K is positive, that means our population is growing. And if our proportion constant is negative, that means we are decaying. Okay, so that's just the setup with it. This model, so think about it intuitively, but the great thing is, like I said, this is always our solution and we can move forward with that. Okay, you don't always have to find it again. But that's it for this video. Thank you for watching, and I'll see you in the next one. Okay.